down this rule number 1, the version number 1. So we all assume, just assume in this context, differentiable functions we're considering here are differentiable. Not only differentiable infinitely many times. Do you know any example of function that if you keep differentiated and it's possible, it doesn't stop at, hey, here's undefined. What's that? E to the x? E to the x is a wonderful example. If you differentiate, is e to the x again, you can differentiate it again. Can somebody find another example? Cube root of x, you can keep differentiating as long as we're staying away from 0. Right? At the 0, it's a vertical line. Pretty much any function you think of that does not involve absolute value is actually infinitely differentiable. So here's an example. What about x to the third? If I differentiate 2014 times, is it possible to differentiate x to the third 2014 times? You are hesitating because after you differentiate 3 times, it becomes 0, right? And then, is this 0 a differentiable function? It's a constant function. It's a differentiable function. Nothing wrong with it differentiating. So it becomes 0, right? Once it's 0, differentiating is 0, 0. Constant function, 0. So almost all the elementary function you know is infinitely differentiable. You can just keep differentiating locally. Yeah. If you have absolute value, you have examples that stop, right? Yeah, except the absolute value. So we have a couple of examples. Was it actually a test problem? The second derivative stops at one point. But locally, they are. Locally, they are differentiable. So we don't state that all the time. So here's a situation. If, so differentiable means it's continuous. So f of a and g of a are both a 0. And we're going to consider g, let's first state that, and then it's happened to have g prime of a is not 0. Suppose you have that situation. And what is the statement? What is the problem we're looking at? The limit x approaches a, f of x divided by g of x. We're going all the way back to the beginning of the semester. Remember? Limit x approaches a, f of x divided by g of x, right? Now remember, limit x approaches a, f of x versus f of a. They're two different things, right? Do you know what happened? F of a, I'm going to write down here as a side note. If f of a versus limit x approaches a, f of x. This is a two different notion. What's happening around x equals a versus what is exactly at x equals a. It's two different things, right? So when is these two things equal to each other? Two different things, when it's equal to each other, it's a property. What is that property called? Most rudimentary level of a property of a function we discussed. Continuity. Get that right. The very definition of continuity at point A is that function behavior around A is exactly the same as the function value at A. That's the continuity. It's not like connected picture. That's everyday notion, and this is precise notion of mathematical notion of continuity. Make sense? So that's what we're looking at in here. So you know, numerator up there, if you look at it here, is numerator is not 0, right? F of x. What happened to f of x? Approaches 0, right? So I introduced this notation. I invented this notation. Approaching 0, not 0, right? Okay. What about the denominator? Approaching 0. So approaching 0 divided by 0, approaching 0. Defined, undefined. Which one is it? Indeterminate form. I just gave you the wrong choices. None of the above was the answer, right? It was indeterminate form. So here's an indeterminate form. All right. Now what do we do? What did we do? We algebraically manipulated, right? If algebraically impossible, we have to use the fundamental theorem of trigonometric limits. If it is exponential, I have to use the fundamental theorem of exponential limits, right? We have to use that. Now we have a different idea. It says, okay, you can just go, if it is a situation, you can actually calculate this. That's how simple it is. No algebraic manipulation, no nothing. You just do this. Okay? Okay, at this stage, after I introduce this one, then I'm going to go through an example. Then I'm going to compare this one with a quotient rule because it's a well-known common mistake. At this stage, all of a sudden, this one becomes mixed up with a quotient rule, right? So first, let's look at the example. This is not the quotient. What is this rule called? L'Hopital's rule. That's what this one is called. Thank you. Right? So, proof. Is linear approximation. So, write down linear approximations of two functions f of x and g of x. At what point? They're all about values around a, right? This calculation we're doing here is the behavior of the quotient when x is very close to a. So linear approximation is good. It's an a here. So let's write Lx is a linear approximation for f of x so that it looks like f of a plus f prime of a x minus a. Is that right? And I'm going to use mx for linear approximation of g of a and g prime of a x minus a. That's the linear approximation. So who remembers about the important theorem that I stated, that it is connecting f of x with Lx? I stated with the TK thing. Right, f of x is T1 here is Lx, right? F of x is a lot like linear approximation. But there is this very special shape of the error term that I'm going to use. There's the error term ex, but there's something multiplied. X minus a was multiplied. That was coming from the denominator of the theorem, right? The approximation theorem, difference between f of x and the approximation Lx divided by the relative input, x minus a, approaches 0. So if you unfold that, you get to in here. That was one of the first things stated in today's class. Okay? What about g of x? And we know this ex is approaching 0, right? What about g of x? It's a lot like linear approximation called mx. I denoted mx here. And same shape of the error term, but it's not the same error, ex, right? So maybe I have to do something else. So I'm going to call maybe fx, or you can use e tilde, some accented notation. So here's fx approaching 0. Is that right? As x approaches infinity. This is the corollary I stated today. The theorem, as it stated, reveals really good that why this is a good approximation, and corollary is good for this type of analysis. So f of x and g of x can be exactly written like this in exact form. It's not arrow. It's exactly like that, with all the complicated part shoved into this ex and fx, and caring only about the property that those ex and fx is approaching 0. Okay? Now this is analytical setup, and what we are calculating here is f of x divided by g of x, right? But before that, what do we know about this information, f of x and f prime of x? What do we know about f of 0, f of a? In the hypothesis, we assume that f of a is a 0, right? So that's actually 0. So linear approximation is a lot simpler than usual. What about g of a? We assume that it's a 0. That's why, so that this becomes an indeterminate form, right? So L of Lx and mx is far simpler. We even know this is non-zero, right? But not as a number, just in that way. All right. So next thing is that, all right, what we're calculating is f of x divided by g of x. Is that right? Now, we don't know much about f of x, g of x, but we know it analyzed like this using linear approximation. Just like when we prove the product rule and quotient rule, this the functional terms is broken into different pieces with carrying this information. So Lx is up there plus x minus a times this error term. Right? That exactly replaces it. And mx, that is the, what is it? Linear approximation of second function, and x minus a times fx, which is the error term for the other function. Now at this stage, you replace Lx with what we know. So what is Lx here? Right, f of a is disappeared. That's assumed to be 0. So Lx is simpler, f prime of a, slope of the tangent line, and x minus a plus x minus a times ex, which is the error term. Denominator, if you look at mx here, ga is assumed to be 0, so that's gone. The g prime of a times x minus a. It's there. That's linear approximation, only one term, and there's the error term, and in exact form like this, not an approximate value, in exact form like this. All right. So you see good things, right? X minus a goes away from each of the term, so you're left with f prime of a plus ex is the error term, g prime of a plus x minus a goes away, and f of x is error term. So there is no limit or anything. It's just f of x and divided by g of x is analyzed into this two quotient in an exact way, right? From here is what rule applies? Limit laws. Somebody said it correctly. Limit laws, right? No L'Hopital's. We're proving L'Hopital's rule. Because ex approaches where? It's 0. This is error term. What about f of x? 0. What about a g prime of a? Approaching something non-zero, right? So it guarantees the denominator is non-zero number, right? Therefore, it is approaching g prime of a, non-zero number, and f prime of a in the numerator. And f prime of a can be 0. As long as the denominator is non-zero, limit law applies. Okay? So linear approximation is unfolding the property of differentiability in a slightly different way, allows you to calculate complicated limit in split second. Right? So that's the power of a linear approximation. That shows you how good this linear approximation is among all the other linear line that looks a lot like the given function. This one stands out. And it's a good application for that. All right? I'll continue tomorrow with more applications of this derivative.